Hello, everybody. Welcome to another lecture of the Regression Analysis course. In this video, I'm going to talk about an estimate of the average value of y for any given value of x. All right, let's pull up everything together. Say we have a simple linear model yi is equals to beta naught plus beta 1 xi plus epsilon I, where y is the dependent variable, x is the independent variable, beta naught, beta 1 are model parameters, and the epsilon term is the error term in the model. The error term is the random component, and so we make some assumptions on the error term, such as expectation of error term is 0, it has constant variance, all EIs are independent and identically distributed, and they have normal distribution. And when we make these assumptions, we get model where the mean of the dependent variable is expressed as a function of independent variable. So we have expectation of yi is equals to beta naught plus beta 1 xi. This gives us a model where the mean of the response depends linearly on the dependent variable. And in this video, we are going to learn about an estimate of this expected value of yi at any given point x naught. But the question is, why do we need to find this estimate? Say we are given a data set, exam score, where exam score is the dependent variable and it depends on the independent variable study hours. And this is how the data set looks like, which is that a student who studied for 4 hours ended up getting 65 points. A student who studied for 3 hours got 68 points, and so on and so forth. And if we look at this data set here, the first observation is that the student studied for 4 hours and scored 65 points. And now if we go to seventh observation, here the study hours of a student is again 4 hours and the student scored 70 points. And similarly, if we go to ninth observation, the student studied for 4 hours and scored 95 points. And if we look at observation number 12, here again the student who studied for 4 hours got 77 points. And now let me ask you all a question. What is the average exam score of students who studied for 4 hours? How would we answer this? The question is asking about the average exam score. Exam score is the dependent variable. And of those students who studied for 4 hours, which means we are not interested in other students' exam score. We only need to find the average exam score of students in particularly who studied for 4 hours, which means that what is the value of expectation of y is the exam score, when x, the independent variable study hours in particular, is equals to 4. And in cases like this, where we want to estimate expected value of y for any given value of x, we are interested in estimating an estimator of expected value of y given x naught. Perfect. So now let's talk about how do we estimate this average value of y when x is equals to some specific value, say x naught. According to our linear regression model, the expected value of y given x naught is equals to beta naught plus beta 1 x naught. But here's the issue. We don't actually know the true values of beta naught and beta 1. Those are the population parameters. So what we do instead is estimate them using our data through ordinary least square estimation method. And we get beta naught hat and beta 1 hat. These are the estimates of beta naught and beta 1 we have already seen. Plugging these value in the equation, we get an estimate of the average response at x is equals to x naught. And this is our point estimate of the average response when the independent variable is equals to x naught. So just to summarize, we started with the theoretical model. Expected value of y given x naught is equals to beta naught plus beta 1 x naught. We estimate the coefficients beta naught hat and beta 1 hat using the data set. And we used ordinary least square estimation method over there. and then we plug in these estimate into the equation to get an estimated average value for y, and that is equals to beta naught hat plus beta 1 hat x naught. Perfect. And we have an estimator of expected value of y given x naught. But here's the thing. Anytime we create an estimator, we want to check if that estimator is unbiased or biased. And before we prove that, let's quickly review the definition of unbiasedness. Let theta be a parameter and theta hat be an estimator of theta. Then theta hat is said to be unbiased if expectation of theta hat is equals to theta. Alternatively, we can also show that expectation of theta hat minus theta is equals to 0. Both the statements are equivalent. We can start by considering theta hat minus theta and then take expectation. If the expectation of that statistic is equals to 0, we say that theta hat is unbiased. And now let's use this definition to prove that the estimate we have is unbiased. So we have the linear regression model at x equals to x naught, which is equals to beta naught plus beta 1 x naught. And we have estimated its value now. An estimate of expected value of y at x naught is equals to beta naught hat plus beta 1 hat x naught. And now we'll prove that this estimate of expectation y given x naught is unbiased. In this case, our theta is expected value of y given x naught, and its estimator theta hat is expected value of y given x naught hat. And now to prove it is unbiased, we will consider expectation of theta hat minus theta. That is expectation of an estimator of the parameter, which is expected value of y given x naught hat, minus expectation of y given x naught. And we know that for any given value of x, in particular, we are taking x equals to x naught, expected value of y given x naught hat is equals to beta naught hat plus beta 1 hat x naught. Expected value of y given x naught is beta naught plus beta 1 x naught. We plug in this value and we get to this result. In the next step, we group beta naught hat and beta naught together, and we group beta 1 hat x naught and beta 1 x naught together. Further, inside the expectation sign, we write the first term beta naught hat minus beta naught as it is. And from the second term, which is beta 1 hat x naught minus beta 1 x naught, we pull out x naught, because in the second expression, we have x naught in both the terms beta 1 hat and beta 1. So we pull out x naught from here. In the next step, we use the property linearity of expectation and get expectation of beta naught hat minus beta naught plus expectation beta 1 hat minus beta 1 times x naught. Again, we use the fact that expectation is linear, and first term we write as it is, which is expectation of beta naught hat minus beta naught. And from the second term, we pull out x naught. And we get plus x naught expectation beta 1 hat minus beta 1. Perfect. So the estimates we have used here for beta naught and beta 1 are the estimates we obtained using ordinary least square estimation method, which is beta naught hat and beta 1 hat. We have already proved that beta naught hat and beta 1 hat both are unbiased. And therefore, we get that the first term expectation beta naught hat minus beta naught is equals to 0. And the second term, which is expectation beta 1 hat minus beta 1, is also equals to 0. And thus, we have that an estimate of expected value of y given x naught, which is equals to beta naught hat plus beta 1 hat x naught, is unbiased. Once we have proved that it is unbiased, the next thing is to find the variance of this estimate. Variance of an estimate of expected value of y at x naught. We have already obtained that an estimate of expected value of y given x naught is equals to beta naught hat plus beta 1 hat x naught. So we have variance of this estimate is equals to variance of beta naught hat plus beta 1 hat x naught. And now we use a property of variance that if we have two random variables x1 and x2, then variance ax1 plus bx2 is equals to a square variance x1 plus b square variance x2 plus twice ab covariance x1 comma x2. In this case, we treat beta naught hat as x1, we treat beta 1 hat as x2, a is just 1 and b is x naught. So if we use this property, we get that variance of an estimate of expected value of y given x naught is equals to variance of beta naught hat plus x naught square variance of beta 1 hat plus twice x naught covariance of beta naught hat comma beta 1 hat. Amazing. So we are using an ordinary least square estimates in order to obtain an estimate of expected value of y given x naught. So these estimates beta naught hat and beta 1 hat are the estimates we obtained using ordinary least square estimation method. And after we obtain the value of beta naught hat and beta 1 hat in one of the properties, we found the variance of these estimates. And we use that property and we have variance of beta naught hat is equals to sigma square times 1 divided by n plus x bar square divided by sx. We have also seen variance of beta 1 hat, which is sigma square divided by sxx. And we have also seen covariance of beta naught hat and beta 1 hat, which is negative 2 x bar times sigma square divided by sxx. And we have variance of an estimate of expected value of y given x naught. And in the next step, what we do is we write the first term separately and group all the three remaining terms together. And we have sigma square divided by n, which is the first term, and all the other remaining terms together, which is sigma square times x bar square divided by sxx plus x naught square sigma square divided by sxx, which is the third term, and the last term, which is negative 2 x naught x bar sigma square divided by sxx. In the next step, again, we write the first term sigma square divided by n as it is. And now the three terms which we grouped together, we factor out sigma square divided by sxx from there. And we get sigma square divided by sxx times x bar square plus x naught square minus 2 x naught x bar. And now in the second term here, which is x bar square plus x naught square minus 2x naught x bar, we treat x naught as a, we treat x bar as b, and we use the identity that a minus b whole square is equals to a square plus b square minus 2ab. And when we use this identity, the first term we would write as it is, and the second term we will write as sigma square times x naught minus x bar whole square divided by sxx. And at the end, we just factor out sigma square from both the terms, and we have a simplified version of variance of an estimate of expected value of y given x naught, which is equals to sigma square times 1 divided by n plus x naught minus x bar whole square divided by sxx.